terms of the universe. So the two, I don't know what color is that compared to that. These are both purple, but that's purple down there. Which kind of purple am I? Yeah, the hydrogen and helium anyway. These top two guys, they were made in the beginning of the universe, Big Bang, and then the blue ones are made by cosmic rays, which are very, very high energy. It's very high energy light, and then the other ones are made in other various ways, like they're made in the furnace of a star. They're made in a supernova explosion. Some of them are man-made. That's these guys right down here that might be new to the table that you haven't seen before. My kids tell me that every once in a while I gotta really get nerdy here, and I got a matching table. I'm really dressed up. It says I wear this shirt periodically. Yeah. I'm matching the table.
Right.
It's not like this one, but it's there.
Close enough.
Close enough.
Underwear to match.
Yeah.
That's right.
Jonah won't let him wear it out of the house.
So let's go back to the beginning here. Here we go. There we are. So same picture as you've seen at the beginning of all the other ones. This session was going to be about how we know what we think we know about the universe. And I have the final tale because I'm kind of following a storytelling model here. Or is it? We don't know if it's the final tale. We're always figuring out new things. And sometimes the pictures that we build for what we see out there are completely wrong. And we got to go back and figure out how to fix them. So I'm going to kind of remind us a little bit about what we talked about last time, then what we can see in the astrophysics lab, and then a light story, pun intended. It's bad. So last time we had talked about science being about building models. That's really what we do as scientists. We observe the world around us very carefully and we make a model. And sometimes we get lost by starting to believe that that model is real. And another way we get lost is we start to think that the only thing that's real is what we can observe with our eyes and our senses. But I'd also mentioned something about the hot buttons of science, and Job 38, 4, verse 7 kind of speaks to me when I think about those times when people get very hot-headed about science and religion not agreeing with each other. I know we're all taught that they're two different books. There's the book of general revelation and the book of specific revelation. They ought to agree with one another, and we have to trust that they will agree with one another. But in Job, that question of whether they agree or not is ultimately unimportant. Because in Job 38, 4, verse 7, God is talking to Job and he says, "Where were you when I laid the foundation of the earth? Tell me if you have understanding. Who determined its measurements? Surely you know. Or who stretched the line upon it? On what were its bases sunk? Or who laid its cornerstone when the morning stars sang together and all the sons of God shouted for joy?" And then there's 4 more chapters of God telling Job, "Where were you when I did this?" Bottom line is none of us was there at the beginning. We don't really know what happened. And so setting ourselves up to say, yes, I know exactly what happened is a little ridiculous. But we still like to build models and we still like to learn things. And if you have the proper focus, you realize that the things you're learning are pointing to God. We're always pointing to the glory of God. That's what God is talking about in Job 38 and following. Look at this stuff I made. Isn't it awesome? It really is. It really is awesome. So, what can we see in an astrophysics lab? This is not a photoshopped picture here. It looks like a happy face. This is a picture that's a combined image. There's an X-ray image in there and an optical image. The optical image has images of stars and galaxies in the background here, but you see these rings here. Those rings are real, Those are multiple, so this right here is multiple images of the same galaxy. And over here, these are multiple images of the same galaxy. What you're looking at is the effects of what we call a gravitational lens. There's some massive object between us and those galaxies that's bending the light around and it's making it act like a lens. You know, if you look through a lens, sometimes at the edges you see funny rings at the edges. That's what we're seeing here. The stuff in the middle was an X-ray image of the sky there, so all the purple light, those are X-rays. You can't see them with your eyes, so we got to put false color on them. And there's two bright X-ray sources in the foreground and a little nose. Makes it look like there's a smiley face here. There's another ring of galaxies that's being lensed by the mass that's between us and the source of light there. So what can we see in an astrophysics lab? I go back to what God said in Genesis, let there be light. I give him credit for that. What we can see in the universe, what we can see in an astrophysics lab is light. That's all we got. We're pretty limited in terms of what we can do with experimenting out there in the universe. All we can do is receive the light passively and try to figure out what it's telling us. That's it. But light can tell us a lot of things here, and I've got a short list of the primary things that we talk about, but there's many, many, many other things that we can throw on that list. I'm going to talk about a few of these today. So one thing light can tell us about is the position. It's pretty easy. You go out in the night sky, you look up, there's a point of light. Oh, the star's right there. I know it's right there. And everybody would agree with you, it's right there. It can tell us the position of the star. It can also tell us the distance, but we got to do a little bit more careful study of that, and I had my wife put pieces of paper on the table just to demonstrate how hard it is to really measure the distance to something that's far away. So if you, I'm going to use Kleenex here. If you take a little piece of that paper, I'm going to make you do an experiment. And you can take turns doing this around your tables and see what you see. But you put that little piece of paper out on the flat surface of the table, and it's going to require you to bend a little bit. I know that might be hard for some of you, but if you can get your eye to the edge of the table, just one eye, close the other eye, and take your finger and try to pinpoint the location of that piece of paper on the table with just one eye. And you're only allowed to look along the surface of the table and try and figure out where that paper is. Once you get your finger down, you can move your head around and see if you can use that to help you find out where that piece of paper is with just your one eye again. So you get your finger down, move your head around. That tells you some information about where that piece of paper is.
Now that we're in this position, we can pray.
Yeah, let's say a quick prayer. The point of that fun little exercise is that it tells you it's hard to, so you can see a point of light along a line of sight. It tells you what direction to look, but you don't know how far along the line of sight it is. When something's really far away, it's really hard to tell. We kind of simulated that situation by making you look along the table surface there and using only one eye. We have this nice innate inborn ability to have two eyes for most of us. That gives us the ability to perceive where things are in the space around us. We have one eye telling us it's over there and one eye telling us it's over there. And where those two lines of sight intersect, that gives us information about where something is relative to us. And when I was telling you to move your head around, you were using what your brain already uses with the two eyes. You were using something we call parallax. You look at something from two different perspectives to locate where exactly something is along the line of sight. So that's the next slide here. So it's easy to say where something is. We receive the light, it's right there. Where along that line is it? Well, we got a nice huge orbit around the sun that changes our perspective every 6 months. And so what I'm showing in this picture here is a bunch of things. The green circle here, that's supposed to be the Earth's orbit around the sun. The little yellow dot in the middle is the sun. And I've got the Earth marked in March, the Earth in September, and we're looking at this red star here. In March, it looks like the star is over here. In September, it looks like the star is over there. And so when we pan to the field of view that we would see from Earth here, in March, it looks like the red star is here. In September, it looks like it's over here. So it's moved from here over to here, and it's an apparent motion. It's not a real motion, it's an apparent motion because of the motion of the Earth around the sun. And so in that way, we're able to triangulate. It's another way to say parallax. We're triangulating the position of the star. We use the geometry of the Earth's orbit and the triangle here. We measure this parallax angle, we call it, to the star. And that gives us a measure of the distance, because once we've got a size of the scale, or the scale size of the solar system, once we know the length of that part of the triangle, we can find out the length of this one using some fancy trigonometry.
Isn't that star moving though?
The star is also moving itself as well, so we have to differentiate between actual motion and the apparent motion caused by the Earth's movement. Yeah. So we have to be careful about that. So I talked about the closest star a few times ago, and mentioned something about this parallax angle. This angle, the largest angle we measure for any star, is a fraction of a 3600th of a degree. It's a fraction of that. We measure these angles in arc seconds, and really we're measuring them in tenths of arc seconds. We can go out to hundredths of arc seconds with our best telescopes. And this closest star, that's 7/10 of an arc second in parallax angle, that tells us it's a little over what we call a parsec away. Parsec is a unit of distance. What it really means is it's about 4 light years away from us. A 4 light year star has that tiny of a parallax angle. It's a very, very small angle, very hard to measure. But we've done it. And we've gone farther out into the universe with this, and we can get out to about 1,000 parsecs, which is about 3,000 light years with this method. We can measure things out to about 3,000 light years distance. And that's as far as we can get with that method. Then we have to use other things about light to help us figure out how far other things are. So we can, using things that we understand here on Earth anyway, we can only get out to 3,000 light years away before we can't really measure the distance accurately anymore. With this method, we have to use other methods. So let me go back to that first slide here. That's talking about position. We can measure the position of a star by looking at the light that comes from it. And we can locate it in the sky. We can also measure the distance to it, at least the method I told you, if it's within 3,000 light years. If we go out beyond that, we have to use other methods that I'm not going to talk about today. Motion's a pretty easy one too. If it's moving across the sky, we have a way to measure that as well, just by looking at where it is in the sky. So one of the other things on the list was composition. We can tell from the light that we're looking at what is out there, what's the star made of. And when my wife was looking through these slides for me and checking them out, she said, "This one scares me." So don't be scared. You don't have to understand completely everything here. I'm just going to tell you about how this gives us composition. I'm going to try to describe what we did here. So this is an image of the light from the star Vega. Does anyone know where to find Vega or what time of season? Maybe a star watcher? It's brave enough. Vega is a summertime star. You see it in the summer. It's one of the bright stars in the summer triangle. It's in the constellation of the Lyre. And it's featured prominently in the movie Contact, but that's another story. Anyway, we're looking at the light from Vega here, and the way that we're looking at it is we're looking at how bright the light is at different wavelengths. So when you look at a rainbow, you're seeing different colors of light. Each one of those colors corresponds to a wavelength. And so what we're doing is we're saying okay, we want to measure this wavelength here. How bright is it at that wavelength? Well, it's that bright. You can see that it's really bright around 5200. This is measured in angstroms, which is a unit of length measure, and angstrom is 10 to the minus 10 meters, if you like scientific notation. It's a small unit of measure. But at about 5200, 5400 angstrom, that's where the source is really bright, and then it starts to get dim again when you go to higher wavelengths. So all we're doing is this is called a spectrum. It's an energy spectrum for these sources. What we try to do is we try to measure how much energy is coming out at each different wavelength of light. And that tells us something about the star, because each of those elements you saw in the periodic table at the beginning of this talk, they have a very characteristic light spectrum that they emit when you burn them. So if you burn those elements, they emit light that you can see, but if you really look carefully at that light, they emit it only at certain wavelengths. So they actually emit lines. They don't emit that rainbow of colors that you see from the sun. They emit specific lines, and you can see here there's dips in the spectrum. Those are lines where light was absorbed by something between us and the star. And we're figuring that stuff was in the atmosphere of the star. So all this light's generated at the center of the star. It's got to make its way outward through all the clouds of gas around it. It's going to absorb some light on the way. And very specific wavelengths of light are being absorbed on the way out. And by those wavelengths that are absorbed, we can tell what element was there to absorb the light. So we've got these H beta, H gamma, H delta, H epsilon lines. There's an H alpha line somewhere in here. I don't see it labeled, but it's right here, H alpha. Those are hydrogen lines. So we know hydrogen's out there in the atmosphere of that star. And then there's other lines that are listed here too. I think maybe boron and maybe, well, I'm not sure what those labels mean, actually. This guy labeled it in a strange way. But each one of those lines tells us about an element that's there at the star. And Vega's spectrum is fairly simple. This is really a simple spectrum compared to some of the other stars. Our own sun's spectrum is pretty complicated. There's lots of lines there, lots of different elements. So depending on the star we're looking at, they each have a different fingerprint associated with them. And we start to classify stars based on what lines we see in the spectrum of light that we could see coming from that star. So we can classify stars, and that helps us kind of put them on a diagram that I'm going to talk about in a little bit. But anyway, so we can tell composition by looking at the light. We look for lines in the spectrum, and that tells us what elements are there. We look for lines of missing wavelengths. So I'm putting this picture up again. We can use the same curve, the same spectrum, to tell us about the temperature of a star. So the shape of this curve has a very characteristic hump shape. That's called a black body by physicists. We refer to that as a black body. We have this model for things that have a temperature. So anything that has a temperature associated with it is emitting radiation. Believe it or not, you sitting here in this room, each one of you is emitting radiation as we sit here because you have a temperature, about 36, 37 degrees Celsius. Hopefully, otherwise you're sick. But because you have that temperature, you're emitting radiation, and the radiation that you emit has a characteristic curve that goes like this. There's a single peak in that curve of the radiation that you emit, or anything emits. The table's emitting radiation, the chairs are emitting radiation, just because they have a temperature. And the way that we figure out temperature is we look at where the peak in the spectrum is. What wavelength does that happen at? There's a very simple relationship between the wavelength of light that the peak of this spectrum happens at and temperature. In fact, if you take the wavelength and you multiply it by the temperature of the object that's emitting the radiation, it equals some constant number. So once you know the wavelength, divide that constant number by the wavelength and you got your temperature right away. So we can use the peak of this energy spectrum to tell us about the temperature of stars out there, or the temperature of other objects out there that maybe aren't emitting visible light, other light. really to be able to determine this spectrum, so this is really invisible wavelengths here. It extends from 3,800 angstroms all the way up to 9,200. On this side, we're probably outside the range of our visible spectrum. The visible spectrum is probably between, well, close to 3,800 angstroms up to about 780 angstroms. Some people can see a little bit farther out, but that's about it that our eyes can see. Our eyes are most sensitive in this wavelength range right here, where you see the rainbow of colors there. To get that spectrum nailed down, we want to look at all possible wavelengths we can look at. And so that's why we have optical telescopes and radio telescopes and X-ray telescopes and gamma ray telescopes. What we're trying to do is really nail down this energy spectrum well, so that we can measure things like temperature and composition. If we look at just the visible light, it's like trying to play the piano with just the key in middle C. That's not a good idea. It'd be pretty hard to do that.
I have a question.
Sure.
Is there anything that doesn't have a temperature?
No. No, everything has a temperature. We've cooled things down to where they're very close to not having a temperature. But they still have a very slight, small temperature, few tenths of a degree Kelvin. The Kelvin scale is the scale that goes, once you hit 0 degrees Kelvin, you don't have temperature anymore. We've gotten things cooled to just above that. So the cooler you, this is a good question, what wavelengths radiation do we emit as we sit here in this room? We emit wavelengths in the micrometer range, so 10 to the minus 6 meters. And your microwave oven is in the microwave region of the spectrum. That's on the order of centimeters in wavelength. And if you cool things down enough, let me see, what does cooler mean? Cooler means longer wavelength. So the cooler you get, the longer wavelength is the light that you emit. So what else can we tell? We can also tell motion from looking at this spectrum, believe it or not. What we do is we look at the lines in the spectrum again. We go back to looking at those lines. And I got some false spectra here. Those lines can shift around. So if you look at these spectra here, I've got, so this line here in the orangish part of the spectrum, it's the same line we're talking about. These lines over here, these three lines are the same lines in this false spectrum that I've made. Those lines can shift around. And depending on which way they shift, they tell us about the motion of that source. Maybe you've heard about the Doppler effect for sound. It works for light too. You know, if you have a race car go by, it goes from a high pitch to a low pitch. That's kind of what we're doing with these light waves. If a source is moving towards us at a high speed, these wavelengths of light that it's emitting, they're going to be shifted towards that end of the spectrum. They're going to be shifted towards the blue end of the energy spectrum. If they're moving away from us, they're shifted towards the red end. So we talk about red shifts and blue shifts. And to astronomers, that means how fast it's moving away from us or towards us. Blue shift means it's moving towards us. Red shift means it's moving away from us. And so we look at where these lines are, and we try to figure out, okay, first of all, we got to figure out what element that is. And then we go here to here on Earth and say, okay, that element emits at this wavelength light. Where is this wavelength shifted relative to that? Is it shifted toward the red end or is it shifted towards the blue end? The amount of the shift tells us the speed that it's moving either away from us or towards us. Again, if it's shifted towards the red end, it's moving away from us. If it's shifted towards the blue end, it's moving towards us. So as you look at this guy, you see this line moving towards the red end as we go forward in time here, and then back towards the blue end there. I got the dates labeled there. So this source is oscillating with respect to us. It goes to moving towards us, to moving away from us. It's going in and out like that. And the way that we interpret a spectrum that does that is that means it's a star that's orbiting another star. Because if we're looking at the orbit edge on, it's going to look like one of the stars is going in and out. Well, both stars are going to look like they're going in and out because they're going to orbit their center of mass. So that's one way we tell about the motion of binary stars. We can measure their orbit period, how long it takes them to get around, by how long it takes to complete one of those in and out cycles in the spectrum. So we use the Doppler effect to tell us about motion towards or away from us anyway. And looking at where it is in the sky tells us about how it's moving across our line of sight. So we got ways to measure both its velocity along the line of sight and its velocity perpendicular to the line of sight. Just by looking at the light. It's amazing. We've got all these models that help us figure that out. So some of the other things on the list: size, mass, and lifetime. How do we tell those things? Well, before we understood the physics of how stars were burning their fuel and stuff, a guy by the name of Hertzsprung and a different guy by the name of Russell came up with this diagram. That's why it's called the Hertzsprung-Russell diagram. Where they were just trying to classify stars. That's what science people do a lot of times. We try to classify things, put them in groups so that we can understand them a little bit better. And on the horizontal axis of this diagram, you have temperature. And temperature is increasing to the left, which is a little weird because usually when you look at a graph, things increase to the right. I don't know why they chose to do that, but they did. Actually, I do know why. It's because wavelength goes the other way. So if you think in terms of wavelength, wavelength is increasing to the right, like normal. Down on the bottom here, we've got these classifications, O, B, A, F, G, K, M. Those are stellar classifications that we put on stars. They were letters that were given. The reason they don't really follow any alphabetical order is because we didn't know what we were doing when we first started classifying them. And so we just put an A on this one, and a B on that one, and a D on that one. And then realized, oh, if I classify them by temperature, then I got to rearrange the letters that I classified the stars. So we left the letter classification the same and reorganized them by temperature. So that's why they don't come out in any special alphabetical order. And as you can imagine, there's all kinds of acronyms to help you remember that classification. I'm not going to tell you any of them. You don't need to know them. Basically, it's temperature on the horizontal axis. And on the vertical axis, it's how bright the star is. So we plot the stars based on how bright they are and how hot they are. And what we found when we started doing that is we've got these stars that are, a lot of stars that are grouped right along this kind of snake trail here. We call that the main sequence of stars. Those are stars that are in the longest part of their lifespan. They sit there for a really long time, and they burn steadily. They don't change their luminosity a lot. They don't change their size a lot during that time. They just keep on happily burning away for a really long time. Most stars in the universe are on that track. And then we saw some stars that were off that track, and so we had to figure out those things too. But so when you plot things sometimes, you can kind of visually see a pattern, and that's what happened with this Hertzsprung-Russell diagram. And then we went to try to use this diagram to understand things like size, mass, and lifetime. So here on Earth, we have this model for if you get something to glow, the amount of light it emits, how bright it is, that's what this luminosity thing is. That's how bright it is, or the amount of energy that it's emitting. It depends on two things. It depends on how hot it is. The hotter it gets, the more light it emits, the more energy it emits. And it also depends on how big it is. If it's got a bigger surface area that's at some temperature, it's going to be emitting a lot more light than something with a small surface area at the same temperature. So if you took two objects at the same temperature, but one was really big, the big one would be a lot brighter than the little one. And so that's where the size comes into play here. If we can measure absolutely how bright any one of these stars are, we can also measure their relative size. If I've got two stars that are at the same temperature, but one is way brighter than the other, that tells me the brighter one's bigger than the dimmer one, because I know exactly how bright it is. So that's the trick. we gotta know how intrinsically bright each star is. And in order to know that, we gotta know how far away they are. So that's why that parallax measurement I was talking about at the beginning, to establish where it is in space from us, is so important. Once we know how far away a star is, we can get to figuring out how bright it actually is, its luminosity. Because we can see how bright it looks, and we know how the brightness of something decreases as you get farther away from the object. We have models for that. Those two things together, how brightness decreases with distance, and how bright something looks, those two things together can tell us this luminosity, this measure of luminosity, how bright a star actually is. So we can do that. We can figure out how bright a star actually is and get it on this Hertzsprung-Russell diagram. Absolute magnitude is also a measure of how bright a star actually is. So we've got two different measures of how bright a star actually is. And so with this Hertzsprung-Russell diagram, if we can place an unknown star on this diagram somewhere, we can start to compare it to other stars that we know about. And we can ask questions about how big is it, how massive is it, what's its lifetime. So we do have models for how stars burn, and that gives us information about the mass of a star. We know that our model says that stars burn hydrogen. They start out burning hydrogen gas. How do you burn hydrogen gas? Well, one way is to mix it with oxygen, but I don't recommend that. The other way is to take it and smash hydrogen atoms together really hard. Really, 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 really hard. And you get them to stick together. When you get them to stick together, that's called fusion, and it actually emits energy. Some of the mass of those two things that you stuck together comes out as energy. That's what's Einstein's thing with E equals mc squared. Some of the mass comes out as light when you stick hydrogen atoms together. Strange, isn't it? Why would it do that? Who knows? But it does. That's our model. And so when we look at these stars, we can estimate their size, we can estimate their mass by how bright they are, and we can estimate their mass by how bright they are because we have information about stars in binary systems, and we use Newton's other law of gravity to tell us how massive the star pair is. Knowing that mass gives us an estimate of, it gives us a way to connect mass to luminosity. We can connect mass to how bright something is. The brighter something is, generally the more mass it has. And so with that mass and with the rate of hydrogen burning, we can estimate a lifetime. We know how fast it goes through the hydrogen gas. That's the amount of mass of hydrogen gas that's there. We can estimate the lifetime of these stars. And we come up with tens of millions of years for some of them, hundreds of millions of years for others. It's a long lifetime based on the burn rate of hydrogen gas in these stars and based on how massive they are. So the mass and the rate at which they burn gas gives us this estimate of lifetime. And a lot of that comes out of this Hertzsprung-Russell diagram. So if we look at this picture here, we've got some stars labeled here along the main sequence. We got some stars that are labeled up here above the main sequence, some stars up here. The colors in the Hertzsprung-Russell diagram that you see here are intended to show you kind of what color you might see if you were able to see the star there. Hotter stars are bluer stars. So if you look at Rigel, which is in the constellation of Orion, that's going to look a little bit bluish, maybe a little white. Deneb's going to have a little bit bluish, blue-whitish color. But if you look at Betelgeuse, which is also in the constellation of Orion, it's going to look a little reddish. And so those colors are telling you about the temperature. The color of a star tells you about the temperature. It tells you where the peak of that curve that I showed you before is. If a star is more blue, that peak is closer towards the shorter wavelengths of light, which are higher energy wavelengths. It's hotter. So blue stars are hotter, red stars are cooler. We got it mixed up when we put the colors on our water taps. Blue's supposed to be hot. So Where these stars appear this way tells you about the temperature. Where the stars appear this way tells you about how bright they are. And you can use the other information that connects temperature and brightness to size to tell you about relative sizes. So if I look at, say, Sirius B here and Rigel, these two guys, they're roughly at the same temperature, not quite. But on the luminosity scale, Rigel is much brighter than Sirius B. So that tells us something. That tells us that Rigel's got to be bigger. It's got to be much bigger in size because it's much brighter than Sirius B. Even though they're at roughly the same temperature, Rigel's much brighter. That means it's got to be bigger. So if you can compare stars vertically, the higher you go in luminosity means bigger star. If you're comparing vertically. If you're comparing horizontally, you can compare temperature. So Sirius B is going to be hotter than Barnard's star there. These stars down here are called white dwarfs, actually. That's where white dwarfs reside on this Hertzsprung-Russell diagram. White dwarfs are really hot, so they're going to appear blue-white if you can see them. And they're not as bright as you would expect them to be, which means they're very compact, they're very small. The stars up here are giant stars. The ones that are kind of towards the red end are red giants. Even these here are considered red giants, even though they're more whitish in color than red. Ones up here are blue giants. So we got all these categories of stars here that tell us about general characteristics, size, temperature, that sort of thing.
I have another question.
Go ahead.
What is the cause then, like a falling star or a shooting star? Is it a change in temperature or?
That's a good question. A shooting star or falling star is really a bit of rock that's hitting the Earth's atmosphere. And it brightens because, yeah, it's getting hotter. It's starting to burn up in the atmosphere. And then when it finally burns up, there's nothing left to burn and it disappears again. So you see this bright streak and then it disappears. And it's burned up at that point.
So it's like a piece of a star then that breaks off? Or
It's a piece of rock.
a piece of rock?
Yeah, it's a piece of rock, really. Yeah.
And so it's not really a star?
It's not really a star. It's a misnomer. Looks the same as a star, but it's not. Yeah. So lots of stuff to tell from light. And here's your quiz here. You got 5 stars on this Hertzsprung-Russell diagram. How's the size of B compared to C?
It's bigger.
It's got to be bigger. That's right. They're at the same temperature, and B's brighter, so it's got to be bigger. You passed the quiz. Good job. All right. I could talk about other things about what we can tell from light if you want me to. I got a little bit of time. Otherwise, I can stop here for questions. I dumped a lot of information. Go ahead, Raj.
Geoff, have we ever, in the brief time we've been able to study stars, have seen them burn out or disappear?
No, that's a good point too. No, we've never seen. Well, that's not true. There have been a few supernovae that we've seen in our lifetime, but they haven't been visible to the naked eye. They've been far enough away or dim enough that our telescopes have caught them. So there was a supernova that went off in 1987. I think that was actually visible in the sky, but it was in the southern hemisphere, so none of us got to see it unless we were vacationing down there. But yeah, we've sometimes caught stars in the act of exploding. But the point is, you're right. When we look out in the sky, really all we're getting is a snapshot. And so I mentioned we can estimate lifetimes, but people also talk about stellar ages, how old our stars are. We talk about the sun being about halfway through its life. It's 10 billion year life, so we've got about 5 billion years left to have it burn quietly for us. How do they do that? And that's hard. We take snapshots, and what we do is we look into the sky and we try to figure out, okay, are these stars grouped together? Yeah, maybe they are. So in this group here, in this group of stars we've got, let's look for the biggest, brightest, bluest star in that group. That's going to give us an estimate of the age of that whole star group, because if that's the biggest, bluest star, that means that stars that were bigger and bluer than that have already exploded. And so they've gone through their lifetime. And so that gives us an estimate of the lifetime of that cluster. And so then we imagine that all the other stars in that cluster were born at about the same time. And that estimates the lifetime. It's a really crude estimate, but it's one way we do it. But again, yeah, all we're doing is taking a snapshot and hoping that our models make sense of things. It's interesting, that question brings up another story. There's a guy at Calvin College, Larry Molnar, who's been studying, well, he's been studying binary systems and asteroids for quite some time now, and he's found a binary system that he's predicting is going to go supernova in the next 3 to 5 years. It would be really cool if someone was able to actually predict a supernova. Nobody's been able to do that before. So he's kind of sticking his neck out on the line there, but it's a cool model he's got. Again, it's a model. Interesting that he can predict that.
I read the story of an astronaut, Russian astronaut, and didn't believe in God. He went to a scientist before 2000. And you believe in God? They all said, no, we're scientists. And then he was an astronaut, and he looked at, and he said, the first man looked at, what did he see? Sun, moon, and stars. Then they got in an airplane, what did they see? The same thing. Then they got in the spaceship, he said, we saw the same thing. Then they go out and 1 light year, 186,000 miles a second, 1 year, and they saw the same thing. And this just keeps going, so they can make a prediction. It just keeps going. And then he went to the scientists, the meeting after the year. And you believe in God? He said, yeah, we're scientists. I thought that was interesting. Oh, then he also said, that blows your mind, it just keeps going. He said, then he turned around 180 degrees. He looked this way. That's the beginning. No beginning either.
Yeah, yeah. It's interesting. Yeah. That's a question. So if you keep on going out into the universe,
Light years.
Yeah.
And finally, they had to make a prediction. If you just keep going, if
what's
you
going to
flip a
happen,
coin,
right?
and they can make a prediction now, it just keeps going.
Yeah.
And he said that changed him to Christianity.
That's interesting.
Yeah. I thought it was just cute.
Yeah. It's interesting because I work with a lot of people that are not Christians, they're scientists. That's kind of the reasoning they give. And there's no reasoning with a person like that in terms of trying to reason them into Christianity or reason them out of Christianity, for that matter. There's just no amount of reasoning you can do to convince them unless you have the action of the Holy Spirit on their heart. So, this guy you talked about must have had the Holy Spirit working on him for a while. He finally came around to the Holy Spirit's point of view.
But if you sit there and start studying it, it just keeps going, our minds. And then the other day, it struck me again, if it keeps going, as God was always there. Always. And then why all of a sudden did he create an earth now?
Yeah.
When all these years, he's just been sitting.
Yeah.
Unreal.
Amazing. Yeah. Yeah. It's amazing. And people can come to exactly opposite conclusions when they look at that. That's the other unreal thing.
Geoff, I wondered when you showed that chart of the location of the sun, is there, as you said last week, the world, how did you put it? You said it's not conducive to life.
The universe, yeah,
The universe isn't conducive to life.
it's,
Life.
right.
And is the sun in that location in the best place for life? Or doesn't that really have anything to do with it?
On this
'Cause it
picture,
just, I'm just seeing the sun in the
Yeah,
center. I don't know
yeah.
if that's the way the chart makers made it or whether.
no, that's just the way it happened. So is it in a perfect location for life? Not necessarily. Actually, the places that people are looking for life are stars down here at this part of the main sequence, because these stars are red, they're very cool, and they have much longer lifetimes because they burn their fuel much more slowly. You have to be closer to the star to be in a region where the temperatures would be right for life, but because of, I mean, this goes along with, you know, this is just all random chance, we got lucky and here we are. You're more likely to develop life on a star that's red like this because it's been there longer. It gives you a longer time to sort of have evolution work its magic and turn things into intelligent beings. That's the model they have. So actually people are looking for life around systems that have stars like this right now. And our sun happens to be up there. Yeah. One other thing about sunlight that's interesting to me anyway is that if you look at this energy spectrum for the sun, the center of the peak is it's right around 5,500 angstrom or so, and it turns out that our eyes are most sensitive to that light. I think that's just an awesome creation that we could have eyes that are most sensitive to the light of the star that we're happening to be orbiting. Other people would argue, well, we evolved so that our eyes were sensitive to that region of the spectrum, but I just think that's a cool occurrence, that our eyes are most sensitive to the light of the sun that we have.
It just makes me think about, I know that Pastor Ed kind of doing Revelation, the study of it, it just talks about the splendor of the light and the glory that we're gonna see in heaven someday, and we aren't even able to comprehend it, because our eyes are limited to
Yeah.
what, it's just
Exactly.
amazing.
Yeah, the part of the spectrum our eyes are limited to it. I was trying to make that analogy before. It's like having just the key of middle C to play a concerto by Mozart. You know, we are so limited in our visual acuity. There's so much other radiation out there that we can't see.
On this chart where you had all the snake trail,
Okay.
is the Earth on there somewhere? Is it like off the chart?
The Earth doesn't appear on here because it's not a star. So we don't classify planets on this chart at all.
So this map isn't necessarily like equate distances between the stars, or does it? Earth is not a star, but I was just wondering, like, you know, where the Earth might fall in that whole constellation of
Right, so
stars.
the Earth doesn't really fall in this chart anywhere, but you can get distance information to stars from this chart if you know something, a little bit more information than what. So like if I want to know the distance to Regulus, for instance, I can look on this chart and see what its luminosity is or its absolute magnitude. And then I can go and look at Regulus with my eyes and say, okay, that has an apparent magnitude or apparent brightness of this. And I can use those two numbers to tell me about the distance to that star from here. Yeah. Planets don't fall on here just because they're not stars.
Mhm.
Yes.
First, thanks for your talks. Secondly, I've been in situations where it might be that I'm talking with somebody and it's very complicated, and the expression will come up, I don't know, it's over my head. Isn't it true that this is over our head?
It may be. It takes some training to understand this stuff. It does, but it doesn't have to be. I don't think it has to be.
When you showed that where that red star was in one spot and then it was in another spot,
Yeah,
can a human eye actually see a star move?
not like that, no. The difference in position is so tiny that we wouldn't notice it. And that's why for so long, people thought, when they look out in the night sky, that it stays the same, it never changes. Because they didn't see the stars wiggling at all.
Talking about creation of heaven and earth. A few years ago when Dr. Nick Cruzy was explaining some of the things about the heavens and so forth. One thing that struck me was he said that sounds really don't end. When you make a sound, it just continues on and on and on. And he said there was a way that they could detect some type of voice associated with the beginning of creating the heavens and earth that kind of trailed off, kind of assuming that, yes, there was a voice there at the time when the heavens and the earth and the heavens were created. You heard anything about like that, Geoff?
I haven't heard anything about that. I don't want to deconstruct what he might have said, but sound is an interesting thing in that it requires something to be there to vibrate. So the way that sound works in this room is there's air in here, and when I speak, my vocal cords get that air vibrating, and that vibration propagates outward through all the air molecules. But out in space, there's no molecules to vibrate necessarily, or not enough to get them to vibrate in any consistent sort of way. And so once you get out to space, there's actually no sound. And so when you see these movies of spaceships flying around in space and things blowing up, and you hear the big, powerful explosion, you wouldn't hear that in space. You'd hear nothing, because there's no sound up there. In terms of other things that we might be able to detect from way at the beginning, there's something called gravitational waves, and they cause ripples in that space-time I was talking about. And so we're actually trying to detect gravitational waves from sources right now, but there is hope that someday we might be able to detect the ripples in the space-time from the very beginning. So maybe that's what he was talking about, I'm not sure. The gravitational waves keep propagating outward, they don't get stopped by stuff. Sound waves, they can get stopped by stuff. They can get stopped by the fact that there's nothing there to vibrate. Gravity waves don't have that problem. Any other things?
Yeah, how can you explain when Jesus was on the cross in the middle of the day, it was 3 hours of darkness?
There's no scientific model that can explain that. It really isn't.
What happened to the light?
Yeah. Indeed, what happened? There's no eclipse that I know of that causes 3 hours of darkness. Yeah. I don't know. It's not impossible for God.
Right.
It's possible for a scientific model to explain it. Well, just FYI, just before I let you go, one of the other things that you can look at with light is polarization. You can look at the polarization of light, and that tells you some information as well. And what I mean by so if you've had polarized sunglasses, maybe if you fish, you wear those polarized sunglasses so you can see through the water. When light propagates around, it's making wiggles, and the direction of the wiggle, if it's wiggling this way or this way or this way or this way or whatever, that's the polarization of the light. If you put those glasses on, it only allows light that is wiggling this way, that's wiggling this way to get in. So when light's reflecting off the pond, the reflected light has been polarized by reflecting off the surface of the water, and it's only wiggling this way when it comes into your glasses. Your glasses say, oh, I'm not gonna let that through. And that's what allows you to see through the reflection into the water on the pond. But that is information that we can use to tell us about what sorts of astrophysical processes are going on in the source of the light. So that's one other thing that we can use. There's also another, we look at light curves as well. How much light is coming out as a function of time. Not enough time to tell you about all those things. Anyway, I think we can be done. Glad to have been here. Thanks for having me.